welcome back. So let's start the week 6. This week 6 is going to be like two parts lectures, and we are going to discuss about the recursion in the first part and the dynamic programming in the second part. Okay. So this week we are going to learn how to program recursive routines and dynamic programming concepts. So these are the really two themes, right? The first recursion and the second one is the dynamic programming. So if you understand these two concepts, then you just completed the objectives. Okay. So to learn how to do this, the objectives are. First, you have to understand the concept of the recursions, and actually many of the recursive programs can be programmed as dynamic programs, right? So actually the dynamic programming is kind of more advanced version of the recursion. So first we are going to cover the recursion, and the second one we are going to cover the dynamic programming. Okay, so to understand the recursion, we have to understand there is a repeating problems, and we are going to define what is repeating problems in seconds. But understanding that is important. And divide and concurrent concepts, and recursive function calls, and recursion escape, and recursion depth, and so forth. Okay, so and after that you have to be able to implement the recursive programs. Okay, and after you've done that, and understanding the concept of the dynamic programming is important. Actually, there is a very important distinction between the recursion and the dynamic programming, and you have to understand that. And after understanding that, you have to be able to implement it. One of the key distinctions between the recursion and the dynamic programming is the memoization. Right, this funny pronunciation, right? It's not memorization, it's memoization. So by utilizing this particular concept, recursive programs, the dynamic programs run more efficiently, time efficiently, by sacrificing some space, memory space. Okay, but as I said in the week 5, time is golden, right? So actually this memoization technique is one of the key things that we learn make our program faster. Okay, so to start with, we have to understand the recursion. So recursion, you know what occur means what? Something happens, right? And if you add re somewhere plus something, means that you are doing it again, right? For example, if I say reoccur, means that that happened again. Something happened again, right? And if I shorten it, recur, right? Recurring concepts, recurring object, recurring items, right? Happens again, right? And added John, so to make it a noun, that's the recursion. Recurring concepts, recurring, something recurs, something happens again and again, that's the recursion. Okay. So for instance, to understand the recursion concept, you have to understand that there are many repeating problems in the real world, and the divide and conquer is the best approach to do that. So what's that? What does it mean? So let's go to the real world example. For instance, let's imagine that we are going to calculate a budget for a year of a company. Means that this company A is going to spend this amount of money, right? And then to find out this company will require this amount of money, then the head CEO of this company has to ask their subdivisions, right? Their divisions to how much will it cost. So the CEO asks the sales department, what's your budget? And manufacturing department, what's your budget? And R&D department, what's your budget? And they will return the numbers. And then by adding up, this CEO will have a budget for the next year, right? So, however, the sales department has many subdivisions. In that case, the sales department cannot determine its own budget by itself. So this department head has to ask again to the branch head, right? How much will it cost for the next year? How much will it cost for the next year? And how much will it cost for the next year? And they will return the numbers, and by adding up, the sales department has its own budget, right? Means that how to handle the CEO's problem, calculating the whole budget, is very similar to the problem the sales department has, right? This department head has the same problem, but at the smaller scale, right? Might be this one has the same problem at the smaller scale, right? So there is a same concept of a problem, but in the reduced size. Same concept of problem, repeating problems. So these are the repeating problems. So company A asks a certain question, and the sales department head is going to ask the same question to the smaller scale, at the smaller scale, right? So that question recurs again and again. So that's the repeating problems. That happens to this guy and this guy as well, right? So in this case, you cannot avoid the below structures. So you have this class department, right? And then you have the sales department as the sales, menu, and R&D. And you have to calculate the budget, right? And then of the smaller, right? Smaller scale, you have to add up. You have to ask the calculate budget at the same time, right? So, So this guy is going to report 10 million won, and this by adding up, this will report the 100 million won. And 300 million won, and 200 million won, and says this company will cost like 600 million won for the next year, right? So it's similar to like if I make it more simpler case. Have you seen these Russian doors? So these Russian doors have the same smaller scale, but the same size, same concept of the doors within inside of these doors. So this big door contains this one, right? And this one contains this one, right? And this one contains this one, and this one contains this one, right? So there is a repeating concept, and the problem the door has inside the same problem, has the same problem inside, right? So that's the repeating problems. And finally, the divide and conquer. I haven't discussed the divide and conquer, right? And divide and conquer is this concept. So company A, the CEO, divides his budget calculating problem into smaller pieces to the sales department problems and the manufacturing department problems and R&D department problems. It's the small scale, the division of his problems. So there is a division, and the divided work is a smaller size, and smaller size. So it means that we divided the problem, and solving the small scale problem one by one, we solve the whole problem. That's the concept of the divide and conquer. Okay. Have you seen the movie Inception? It's like the 2 years ago there was this movie, and Leonardo DiCaprio and I remember Aaron Page and others were there, right? Others starred in the movie. And in the movie Inception, the concept is that there is this person, and there is this person's brain, and we want to go inside of that person's brain. But and that person's brain has this like dreams, right, like this. And inside of dream there is another. So there is a one person again, and he has this dream inside. And within the dream there is this person, and there is a dream inside, right? This. So actually, in the true real world, here Leonardo DiCaprio and another girl is living in peace, and then he enters someone's head and in the dream, and then there's someone's dream. In the dream, we have like this another person, and then DiCaprio enters his dream, and then within inside of this dream, and there is another man. We can go into another man's dream, another man's dream, another man's dream, another man's dream, and finally there is some certain kind of the very fundamental of someone's perception, and we are going to implement some kind of concept in that someone's head, and then we are going to call it as Inception. Anyhow, it's interesting movie, so I recommend you watch that. Why I'm telling you so much about this movie is because that this recursive concept is very similar to this idea: dreams within inside of dreams and within inside of dreams, dreams within dreams. That's the recursion. So characters dream when they are still in a dream. So things like that. I go to bed, and then I sleep, and then within my dream, I again dream, and within my dream, I dream again, and things like that. So there is when characters dream when they are still in a dream, there is an increasing layers of dreams. So that's the real world, and this is dream 1, and this is dream 2, and this is dream 3, and this is dream 4, and this is dream 5, and this is dream 6, and that's the depths, right? There is the depth 0, and if we go inside, we can reach to the depth 6, right? And within the dream, these characters, because there are so many layers, someone is conscious, but he might be conscious in a certain dream layer. In that case, he wants to know whether he is in a dream or not. To identify that in the movie, they use these characters, these movie stars, or the characters in the movie, utilize these totems. These totems tell you whether you are in a sleep or not. Means that this totem will tell false, because that this one is in the real world, it's the true real world, so he will tell, this totem will tell is going to be false. Here, this totem is going to tell the true, and this totem will going to tell true, and so forth. And what you are going to assume that is that let's imagine that this totem is a little bit smarter, so totem can tell you, let's imagine that this totem can tell you which depths you are in, like you are in depth 0, and depth 1, depth 2, and depth 3, and depth 4, and so forth, right? Then by checking that whether the depth is 0 or not, we can identify whether you are in a real world or not, right? And finally, there is a mechanic called kooc, right? Characters awake from one layer of their dreams by utilizing the kooc. So someone can go to bed and sleep, and then he dreams, right? It's very natural concept. So if you are in sleep, you can move to the next layer of the dream and sleep, right? And sleep, and so forth. And this kooc is a method to get up to one layer, right? So we are going to say it's kooc. It's awake, when we are awake, there is a kick, and then someone's conscious gets one layer up, closer to the real world. There is a kick and kick, okay? So sleep, 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 kick, kick, kick. These are called the inception, like the concepts in the inception. And very interestingly, these ideas in the movie Inception is very similar to the concept of the recursion, right? Let's find it out. So we are done with the movie, and we are going to deal with a very simple example called factorial, right? Do you know factorial numbers, right? The 5 factorial means 5, 4, 3, 2, 1, or multiplied, right? So then if n is 0, right? 0 factorial is just 1, and n is going to be bigger than 0, so it's 1 factorial is just 1, of course, and 2 factorial is 2 because multiplied by 1, and 3 factorial is going to be 3, 2, 1 means 6, all right? So it's very easy to compute. It's a very simple example. And if we are going to show this as a mathematical concept or mathematical formulas, this is the right description, right? Having said that, and with the knowledge that there is a concept called recursion or repeating problems, can you find any repeating problems here? Of course. Any repeating problems? There are. Factorial n can be described this as well. 1 and n, and this is actually the factorial n minus 1. So that's this, right? N multiplied by factorial n minus 1. So to solve a bigger problem, you just solve one smaller problem, and you do these small things, and then you solve a bigger problem. So it means that if you want to solve this big problem, you have to divide it or make this problem little smaller and little smaller and little smaller. And when you reach the factorial of 1, then you know what's the number of that. Or if you reach to the fact 0, of course, there is a clear definition of this, and then you can wake, or you can use the kick in the word from the movie Inception. You can use the kick, you can use the kick, and so forth, right? Let's clear things out a little bit further. So because it's very important concept, I'm going to repeat this again, okay? So let's say we are going to calculate factorial 4. In that case, what you are going to do is making this problem a little smaller. So 4 factorial 3, right? Means that, and to solve F3, we need F3 is 3 multiplied F2, right? And write this. And to solve this, F2 is 2 F1. Like this. Okay. So to solve F1, F0, right? And to F0, actually, there is this condition that F0 is always going to be 1. Right? And it's going to be always 1, so it returns 1, right? And this returns 2, right? And this returns 6, and it's going to be 24. So moving down is dreaming. Moving down is dreaming. And moving down is dreaming. And by figuring out this F's number, we can go upstairs, upper layer is going to be called kick, and it's going to be called kick, and this is going to be called kick. These are all using the keywords from the movie Inception. So you now understand why I introduced about the movie Inception, all right? So this is how we are going to solve the factorial problem. Of course, someone may already say that why don't we just utilize the for loop, right? For loop from 1 to n, multiplying all these numbers. Right, you can do that, but I'm just trying to explain to you the factorial problems with the repeating problem concept. So that's why I'm taking the tour, right? And then the great common divisor, we have this, and to solve this, and actually there is a very interesting algorithm called Euclid's algorithm, and how to do that is this. So for instance, we are going to utilize these two concepts, right? So 32 and 24. This is going to be G, and this is going to be same to the G, right? And the 24 and 32 divided modulo 24 is going to be is in Korean 나머지, in English modulo operation. So it's going to be 8, right? And this is actually the same problem of what? 8, 0, right? And after hitting this format, A, 0, then A is the GCD. So here is going to be 8, right? And that's how we solve the problem. And this is the recursion, and kick, right? So make the problem smaller pieces, and when we solve the small piece, and we go upstairs, and we return the value. That's how we handle the problem with the recursive concept, right? So this commonality, common things in this problem solving concepts is that there is a repeating function calls. To calculate f, we have to call this function again, call this function again, call this function again. So there is a repeating function calls, and there is a reductions in parameters size, right? When we are concerned for the parameter size were down to 3, and to 2, and to 1, and to 0, right? So there is a repeating reducing size of the parameters, right? 30 to 24, 24, 8, and 8, 0. So there is a reduction. And if you recall your high school days, this is very similar to the mathematical induction in Korean 수학적 귀납법, right? So it's very similar to the concept of the mathematical inductions, right?